All right, this video is going to be on how to find the derivative of an inverse. So first we're going to go ahead and write down a little statement about when an inverse would even exist. So we're going to say if f has an inverse, and we're going to call the inverse g, we're going to rename it. So if f has an inverse and that inverse is g, then g is differentiable at any x for which f prime of g of x does not equal 0. All right, and we're going to address a little bit more of that when you guys come to class when we talk about it. So go ahead and leave yourself space here because we are going to write something. We're going to add something to our notes here, and then we're going to go ahead and start the example down here. Okay, so first example, we're starting off with the function 2x squared minus 4 for any x that is greater than or equal to 0. And we're going to do three different things with this problem. First, we're going to find the inverse. Let me write the instructions correctly. We're going to find the inverse. And us finding the inverse is actually why we limited the domain of this problem. This is a parabola. And this tells us to only use the right side of the parabola because if we did not limit the domain, then the inverse of a parabola is like a sideways parabola, and that wouldn't pass the vertical line test, and so it wouldn't be a function. So when they limit the domain on this, they're telling you that you're using only half the parabola, which means when you find the inverse is actually a function instead of just being an equation. So first we're going to find the inverse, then we're going to go ahead and we're going to find the derivative of the inverse. So f inverse prime of x, that's the derivative of the inverse. And then last, we're going to find the derivative of the inverse evaluated at a number. All right, so let's go ahead and start part A. So if I look at this, I can see that to find my inverse, I need to do what I learned in those math classes way back in the day, and I just have to trade my x and my y value. That's all that's really required to find an inverse. But we typically like for our equations to be in y equals form, and so now I'm going to go ahead and solve for y. So I'm going to add the 4 to the other side, and then I'm going to divide the 2 over to the other side. And then I'm going to square root. And normally when I square root, I would put a plus or a minus in the front. And the plus would be using like the top half of the square root, and then the minus would be the bottom half, and that's what would make that sideways parabola. But we did limit our domain, and so that means we're going to limit this to only the positive version. So I'm going to go ahead and leave it just like that. And then I'm going to say that f inverse of x is the square root of x plus 4 over 2. So there's my inverse function. Next, I'm going to go ahead and find the derivative of my inverse function. And so it's going to be a little bit easier if I rewrite this problem. I'm going to think of it as something to the 1/2 power. X divided by 2 is kind of like saying 1/2 x. 4 divided by 2 is 2. So to find the derivative, I need to do the chain rule. So I'll bring the exponent to the front, keep the inside the same, take the exponent and subtract 1 from it, and then I'm going to multiply by the derivative of the inside. And so that gives me 1/4. And then I do have that square root on the bottom. So I could write this as 1/2 x plus 2 like I'm doing, or if you wanted to go back to that original notation, you could do x plus 4 over 2, and that would be fine. We know that this is not really a very proper answer written the way that it's written, and so you could rationalize it by multiplying this by the radical over itself. We'd probably want to pull out that fraction to make things a little bit more proper. Um, but I'm going to go ahead and leave it just like this. All right, so part C is now telling us, let's go ahead and take that derivative of the inverse and let's plug it in for x equals 2. And so f inverse prime of x, sorry, we're evaluating it at 2, is 1 over 4 times the square root of 1/2 times 2 plus 2, which is 1 over 4, and then 1/2 times 2 is 1, 1 plus 2 is 3. If you were doing this answer, they would definitely rationalize that for a multiple choice. So I'll go ahead and fix that by multiplying by root 3 over root 3. And so that gives me root 3 on the top, and then on the bottom 4 times 3 is 12. Okay. So let's go ahead, before we move on to the next problem, I do want to show you something, not because it was necessary on this problem, but because it's easier on this problem and we have to do it on the next one. So this information right here says we're taking the inverse and we're plugging in an x coordinate of 2. So I'm going to go ahead and write this. We have the inverse function, we're plugging in an x coordinate of 2. So if I plug an x coordinate of 2 just into the normal function, then it would give me some sort of y coordinate, okay? And if you probably weren't thinking like this, but that means that if I plug in whatever this y coordinate is, if I plug this y coordinate into the original function, then the output is actually going to be 2. Because when we do inverses, the inputs and the outputs kind of change. All right, so what I'm going to do real quick is I just want to see what that y coordinate would have been. And so I'm going to say for the original, I guess I shouldn't have written it down here, I should have written it up there, but I'm going to go ahead and plug in 2x squared minus 4, and I just want to see what x value gives me a y value of 2. So I'm saying y equals my equation, y equals 2. I'm going to go ahead and graph those. Now, because we're using the part where it says x is greater than or equal to 0, I don't want to find both of those intersections. I just want to find the one on the right. So, okay. So this value right here is actually, I believe that's the square root of 3, 1.732. Square root 3, 1.732. So if I plug in the square root of 3 to the original function, I get 2 as an output. If I plug in 2 to the inverse, then I would get the square root of 3 as an output. And we can go ahead and verify that. I guess this one would have been the easier one to plug into all along. But if I do square root of the fraction 2 plus 4 over 2, then I get 6 over 2, which is 3. And that's just the square root of 3. Okay, so it's just good for us to remember that these, we can just kind of trade those, and that's how it works. And you'll see why in a second. So let's go ahead and do the second example, which is going to be a little bit less straightforward than the first example was. So example 2, we're still going to do all the steps that we did. We're still going to start with a function. And we're still going to say find the inverse. And then we're going to say find the derivative of the inverse. And then we're going to go ahead and last, we're going to find the derivative of the inverse evaluated at 3. Okay, so let's start with step A, part A, I mean. So to find the inverse, we just have to trade our x's and our y's. So x equals 1/4, y to the third plus y minus 1. And this is one of those cases where we cannot solve for y. Just can't do it. So I'm going to say I'm done. And since we could not solve for y, that means that this is not like f inverse equals. This y right here actually represents our f inverse of x. F inverse of x is just kind of like hidden in the problem. We can't solve for it, but we know that it's there. Okay, so part B says now find the derivative of the inverse, and this is why we learned how to do implicit differentiation first, because now we have to find the derivative of this inverse. All right, so basically we have to find the derivative of y, which is implicit differentiation. So let's go ahead and do that. Derivative of x is 1. 3 times 1/4 is 3/4, y to the second, and now we're going to do times dy dx. So if y represents the inverse, then the derivative of y represents the derivative of the inverse, right? And then we have plus 1 dy dx, and then minus 0. So just like normal implicit differentiation, go ahead and solve for dy dx. So I've got 1 equals, I can go ahead and ignore that. I've got dy dx 3/4 y squared plus 1. All right, and then to solve for dy dx, I'm going to have 1 divided by that whole fraction, 3/4 y squared plus 1. All right, so I can write that as dy dx, or if I want to change the notation, I could now say that that's the derivative of the inverse. So I couldn't isolate the y to get the just the inverse, but I can say, okay, I've isolated the derivative of the inverse at least. It just happens to be written with no x's. It just happens to be written with y's instead. And this y right here is representing f inverse of x. So there's our derivative of our inverse. Okay, and then part C says we need to find the derivative of the inverse evaluated at 3, and that 3 right there is an x value. That's x equals 3. Okay, so this notation is saying if I have the inverse function, I'm plugging 3 in for x, and my result is some y coordinate, which means I have to go back to the original, and I say for the original, if I plug in some x coordinate, I get a 3 for y. Okay, now when you look at this, our derivative is only in terms of y, there's no x there, so I can't plug in 3 because I'll get the wrong answer. So what I need to do is I need to go up to my original equation. I need my original equation to equal 3. So I'm going to say 1/4 x to the third plus x minus 1. I need this to equal 3, so I'm going to figure out what input gives me an output of 3. So if I plug in 2, I get 3. And so that means if I plug in 3 to the inverse, I get 2. So now if I want to evaluate my derivative, you can write this notation or you could write this notation. I think this notation might make a little bit more sense. So we could say dy dx is evaluated at an x value of 2 or a an x value of 3 and a y value of 2. And then we can plug everything in. Or if we stick with this notation, then we're just saying f inverse prime of x is 1 over 3/4, sorry, not of x, of 3. And then it doesn't tell you that the y-coordinate is 2, but the 2 is implied because that's the y-coordinate that corresponds to that x-coordinate. So if you are more comfortable writing it this way, you certainly can, as long as we're saying, you know, that the derivative is the derivative of the inverse. And so that gives us 2 squared is 4. So we have 3/4 times 4. That means that the 4 is going to cancel out. And we have 1 over 3 plus 1, so this is going to give us 1/4. Okay, let's go ahead and do one more problem. So we're going to say the function is f of x equals 2x plus cos x, and we're just going to walk ourselves through those same steps. So first I'm going to find the inverse by trading the x and the y. And I cannot solve for y there, so I'm going to go ahead and just let that be my inverse function right there. Then next I need to find the derivative of the inverse, and I'm going to do that using implicit differentiation. So the derivative of x is 1. The derivative of 2y is 2 dy dx. The derivative of cos y is negative sine, keep the inside the same, times dy dx. And so I'm going to go ahead and factor out the dy dx. 2 minus sine y. And then to get dy dx alone, I'll take the parentheses and divide them over to the other side. So dy dx equals 1 over 2 minus sine y. And you can write dy dx, or you can say f inverse prime of x And honestly, I might have to look into that. I don't know if that notation is okay since it's not really in terms of x, it's kind of in terms of y. You might have to stick with this notation actually. All right, and for the last part, we're going to go ahead and we're going to find f inverse prime of 1. Okay, so this is saying we have an x value that is 1, which means if we are thinking this through, that the inverse function had a 1 that was plugged in and then it gave us some y-coordinate. So if we go back to the original function, that means that there was some x-coordinate that was plugged in that gave us a y-coordinate of 1. So I'm going to go back to the original equation. And whenever you use your calculator with a trig function in calculus, we always use radians as our mode. So make sure you're in radian mode. And then we can go ahead and graph it. I didn't make it 1, it's still 3. So I'll fix that in a second. Make it equal 1. Okay, so if I find that intersection, then that x value is 0. So if I plug in 0, I get 1 for the original function. That means for the inverse, if I plug in 1, I get 0 as the result. So if I want the derivative of the inverse evaluated at x equals 1, then I really want dy dx evaluated at the point 1, 0. 1 for x, 0 for y. So this is 1 over 2 minus sine of 0. And if I think of the unit circle, here's 0 pi radians right there at the point 1 comma 0. And so sine of 0 is just 0. So this is 1 over 2 minus 0, which is 1/2.